All right, then perhaps I think we can, now we've done that nice tour du table, a virtual tour du table, I'd like to say a very warm welcome to everybody for this second News from the Lab. So the aim of this event is for you to be able to reconnect with the organisation, to bring you back to CERN, even though at the moment it's just virtually, and to give you a privileged insight on the activities that are taking place, so that then you can spread the word amongst your friends and family about the important work that we're doing at CERN, and you have been also involved in this work in the past. Today, I'm delighted to introduce Dave Barney, Dr. Dave Barney, who is CERN Principal Applied Physicist for the CMS collaboration. Dave, there are plenty of things, there's lots in Dave's bio. I'm not going to say it all. You can go to the alumni.cern platform to the event and you can read all of the of Dave's achievements there, but I'm just going to highlight a couple of them. So Dave was CMS Educator and Outreach Coordinator for more than a decade, and has also led the International Particle Physics Outreach Group. He now leads the CERN EPCMX group and is actively involved in the High-Granularity Calorimeter upgrade. Our moderator this evening is Dr. Rebecca Gonzalez Suarez. Hi, Rebecca. So Rebecca was also a member of the, again, a very nice bio that you can go and see on the alumni.cern platform. Rebecca was a member of the CMS collaboration and was stationed at CERN for more than a decade. But then Rebecca moved in 2018, I think, to Uppsala University with a starting grant from the Swedish Research Council, and she joined the Atlas collaboration. She switched sides. Along with her many professional activities, Rebecca was elected Outreach Coordinator for the Atlas collaboration and has been in charge of Atlas-wide education, communication and outreach since the 1st of March 2021, along with all the other activities that she does. You're in for an absolute treat tonight. So just to give you an idea of how the event's going to take place, we'll have about 30 minutes presentation from Dave, and then we'll kick off with a 30-minute Q&A. So when we have the Q&A, please come on camera and ask your question on camera. If you're a little bit shy, you can also put your question in the chat. So I think, Dave, can I hand over to you, Dave and Rebecca, please? Well, Dave first.
Sure.
Your presentation. Thank you very much.
Okay, so hopefully you can see the screen. It seems to be the regular thing we do now, is ask if anybody's out there and can actually see the screen. Thanks for the introduction, Rachel and Rebecca. I'm going to try and give you a very brief overview of some of the things we're doing at CERN at the moment, focusing on the thing I'm now working on, which is called the High-Granularity Calorimeter. In fact, I've been at CERN now for a long time. I've been here more than 25 years. I received my wonderful CERN pen just recently to say that I've been here for 25 years. And all that time I've been working on CMS. And probably until I retire, I will continue working on CMS. So it doesn't get boring. It's still great. And yeah, I'll show you through some of the things we're doing now. So as many of you know, so not so long ago, back in 2012, there was the announcement of the discovery of the Higgs boson by Fabiola and by Joe. Of course, what actually happened was that CMS discovered it and then Atlas confirmed the discovery, which was very nice of them to do that. And then Fabiola became the Director General of CERN a few years ago and is still in that position. So this was a big deal, of course, back in July 2012. And it became quite well known. Estimated worldwide audience of about 1 billion people witnessed this announcement all around the world. I was in Melbourne at the time attending a conference. And of course, a couple of years later, the Nobel Prize was awarded to 2 of the people who came up with the theory about the Higgs boson, including Peter Higgs himself. So that was sort of the big event over the last decade. Now you can see some of the big numbers. Of course, CMS and Atlas and CERN in general are filled with big numbers. like the amount of data that we've now collected, 280 petabytes of data roughly, pales into a bit of insignificance compared to Facebook, but in scientific terms, it's an enormous amount. We've had nearly 40 quadrillion collisions, and I had to write down all the numbers of all the zeros so you can actually see how many that is. But importantly, we've actually created in the LHC about 8 million Higgs bosons now. That doesn't mean that we've discovered them all or measured them all, but we've created a lot of them, and a fraction of them we've actually managed to detect in CMS and Atlas, and then try and do something with them, try and explore them a bit more, try and find out how they behave. So if you look at CMS as an example, so I do apologize to present and past Atlas people. I'm going to focus entirely on CMS now, apart from one part. This is the number of papers that CMS has published on the Higgs as a function of time. And you can see there are a couple of papers back in 2011, but then things really took off once we announced the discovery. And then has continued really quite dramatically over the years. And I know Rebecca was heavily involved in the analysis of many of the things that led to the papers on the Higgs here. So about 140, 150 papers just on the Higgs over the past decade. If you look at all of the papers from CMS, we're more than 1,000 publications on a variety of different things, including standard model physics, but also covering more exotic things. So let's say exotica and supersymmetry. So these are mainly searching for new physics, looking for different things out there that we don't already know about. So you look at this light blue one at the top here, which is what we call exotica, looking for new physics, and supersymmetry, the green one. There's a huge number of searches for different phenomena. As yet, we haven't really discovered anything new or anything dramatically new like the Higgs was. It doesn't mean that there's not a lot going on, as you can see from the papers. And in fact, there's a conference ongoing now in this place called Morillon. Well, virtually Morillon at the moment. And there's a couple of things here like searches for heavy Higgs bosons or heavy ion physics as well, looking for different things in CMS, and some very nice measurements that have been done. So as I say, so far, no new physics. Now I say that tentatively, because in fact, in the last week or so, some of you may have seen, there's been a new paper published by LHCb that points to something quite new. Okay, it's not that new because LHCb had already published a few papers in the past that points to, you see this, this plot on the right. This is showing essentially the ratio of decay of B quarks or B mesons into different phenomena, one into pairs of muons and one into pairs of electrons. And the theory says that they should be the same. So you should get a ratio between these two things of 1. And what they're measuring is not 1. It's pointing to something new. Is there a new force at play? Well, only time will tell, but this is quite exciting. This could be something very, very new. But there's much more than that. There's lots of questions that we don't actually have virtually any understanding of. Now, LHCb is focused on studies of antimatter and the differences between matter and antimatter. But CMS and Atlas are also looking at those things. There's the question of mass. We now have a bit of an understanding of that with the Higgs boson. But then there are things like dark matter. What explains most of the matter in the universe? We just don't know. And then there's this mysterious force that's causing the universe to expand faster and faster that we imaginatively call dark energy. So, and then of course there could be, what else? Things we just haven't really thought of yet. So CMS and Atlas especially have got a long way to go yet before that we actually come up with some answers to some of these basic questions about the universe. To do that, what we've actually got is in CMS, we've got this, the most attractive, most photogenic, most amazing detector ever made. We call CMS, compact muon solenoid. And, oh, sorry. In fact, a large fraction of my career was focused on this white disc here, one of these small parts of it called the pre-shower detector. I spent about 20 years of my life designing this, operating it, building it, and so on. And I'm still responsible for it, in fact. So this is a picture of CMS in the cavern. And we'll come back to that later, especially this part here. Now, CMS isn't something that just stays constant with time. In fact, we can't let it get old, in a way. A few years ago, we went through what we call a phase 1 upgrade. So we changed a few parts of it. In particular, we changed the most inner detector, called the pixel detector. And we also upgraded the Hadron Calorimeter, this part that's highlighted in yellow, to have new photo detectors, so new things detecting the photons from there, to improve efficiency, to improve stability. And we upgraded the electronics that read out these detectors as well. We also upgraded this part at the front, we call the forward Hadron Calorimeter. We also, apart from detector upgrades, we modified the trigger system. So this is the thing that determines whether you have good events or not, the thing that makes the decision what to keep and what to throw away. Again, increase efficiency and store more good events. And it's all worked rather well. This plot here shows the different parts of CMS, from the tracker on the inside to the electromagnetic calorimeter parts, Hadron Calorimeter parts, and then the muon detectors. And this is the fraction of those detectors that still work. And in fact, it's measured before and after what we call run 2. So it's between about 2015 and 2018. And some things have gone down, but some things have actually gone up. So for example, the bit I'm responsible for, the pre-shower, we actually managed to fix a few things, and it's effectively now working at 100% level. So it's all very efficient. Mostly what goes wrong are not the high-tech parts. They're all the low-tech parts, all the things that you have in your home as well, things like power supplies, connectors. You can repair. Some of them, they're just embedded too far in. It's like having trying to fix something that's on the moon. It's just, it's impossible to fix. So connectors are one of the banes of our life, in fact. And we're just beginning to recommission the accelerator complex at CERN, especially with the proton synchrotron and the super proton synchrotron. At the end of this year, at the end of 2021, we'll have a so-called test beam. We'll get the LHC working again just briefly for about a week, make sure everything is working okay, and then we'll start operating again in the beginning of 2022, run for about 3 years, and then we'll go into long shutdown 3, and that's mainly what I'll talk about. And then after that, we'll run again. And the life for this part from 2028 onwards, it only goes to 2036 here, but it will really go to about 2040. Will just get more and more difficult. The reason it will get more difficult is the complexity of the collisions will increase. So back when we first started operating, a typical collision in CMS looked like this top image. So we had every time we get protons colliding, we don't just hit one proton against one other proton, we hit multiple protons. And that number, that multiple, has increased with time. So in 2010, there were roughly 2 protons colliding every time. 2011, that went up to about 10. 2012, up to about 30. We're now running around 50. We'd actually designed the whole detector for about 20. So we're already running beyond the design spec. in the next phase, what we call the high luminosity LHC, from about 2028, this goes up to about 140. So things become really very difficult indeed, and probably much higher. In addition, or accompanying that increased number of collisions per what we call bunch crossing, it comes with radiation. So the radiation is damaging our detector, and particularly in the forward regions. And the plot on the right shows in the NCAP regions how the radiation will be extremely high. In fact, to levels that we actually have currently in the innermost detectors, like in the pixel detector. The upshot of that is that the detectors in the end, on these NCAPs, will just not survive this amount of radiation. They just can't. And this simulation on the left is showing the signal size coming out of the NCAP electromagnetic calorimeter, this part here, as a function of time. So what we call 3000 inverse femtobarns is the end of lifetime of the HGCAL. And effectively the signal goes down to about 0. So we just won't see anything from these detectors. So we need to replace it. In fact, the NCAP calorimetry is only one part of what we need to upgrade for CMS to survive and be functional and performant throughout the lifetime of HGCAL. So we'll replace the inner tracker, we'll replace the NCAP calorimeters, we'll replace the trigger, the high-level trigger and the data acquisition system fully. But then all of the other detectors will modify their electronics to cope with the higher collision rate. We'll also add new detectors, so-called MIP timing detectors, which might feature in a future edition of this News from the Lab. So there's a lot going on. The bit that I'm really working on now is this replacement of these NCAP calorimeters, so this part here. And we aim to install this in about 5 years from now. In a way, what we're now trying to do is go back in time. So we used to have detectors at CERN that really visualized interaction. So this is a bubble chamber photograph from the early 70s. And you could really see what was happening. You could see particle interactions, you could see particle decays. So you got this pictorial representation. What we aim to do is to do the same sort of thing with this new calorimeter system, to instead of seeing just the bare minimum, we actually want to try and go down to really the details of every particle that we create in these particle showers, in these collisions, and differentiate them and really understand the details of the physics. If you like, you know, it's like trying to move from an old style photograph where you had very little information into something where you could really see who's actually dancing there or attempting to dance. The way we plan to do that is quite hardcore in a way, which is we're going to essentially cut off this whole detector system on the NCAPs of CMS as about 220 ton object, take it off in one piece and then replace it with something new, which is our so-called high granularity calorimeter. Now, why is it called high granularity? Well, I'll come to that in a minute. Essentially, because we want to get more information out of it. Now, about the high granularity calorimeter, one of our spokespersons came up with this quote, and he said, when we decided this was what we wanted to build, there are no showstoppers, it's all just engineering. To which someone a bit less wise said, this is probably the most challenging engineering project that we've ever undertaken in particle physics. Now, we can say that very often because we're always pushing the boundaries, but I think in this case, it's definitely true. And if you look at some of the challenges ahead, it's essentially mobile phone technology, but on a massive scale, on the area of about 4 tennis courts. It has to work effectively and efficiently without any intervention. We just can't repair anything. Once it's installed, that's it. It has to operate around -30, maybe -35 degrees C, in a radiation environment similar to being in the core of a nuclear reactor. And the amount of data that this just one detector will generate is equivalent to about 1 million mobile phone photos per second. So it's an incredibly complex and challenging device. Where do we start with such a thing? Well, first of all, we need to be able to afford it. Actually, it's a very mundane comment, but that's where we start from. We need to be able to pay for this. So low cost per unit area materials. They then need to be adequately radiation hard to survive these conditions that I mentioned earlier. And going from that, what it led us to essentially is something based on silicon detectors. Now, silicon detectors are more commonly used in trackers, not in calorimeters. In fact, until now, there's only been a handful of them, of which the pre-shower that I mentioned earlier that I worked on for many years was the biggest example. And until then, that was the biggest silicon-based calorimeter in the world. It had an area of about 16 square meters. Okay, so this is what we're basing the HGCAL on. Now the HGCAL is something quite different. We're going to be using not 16 square meters, but 620 square meters of silicon. This is about 3 times the area of the present CMS tracker, to give you a feel. But this is embedded in 220 tons of dense material. We also have about 400 square meters of Scintillator, so a different type of detector. And there's a massive power budget as well, 125 kilowatts of power per endcap that we have to evacuate. We have to get it out. Otherwise the thing will heat up and melt, which we really don't want to happen. The way we're arranging this, sorry, I should mention, all of these green lines, these vertical lines, represent individual layers in our detector that are made of silicon. So in fact, there's 28 layers in this first part, the so-called electromagnetic part, or CEE, we call it for short. And then there's more layers in the back part that measure hadrons. But they become more complex because we couple these layers with Scintillator as well. So some of the layers are a mixture between Scintillator and silicon. But there are many, many layers here, up to 50 layers. In fact, we've now gone down to 47 in the last week. We made a decision to simplify things a little bit. The way that each layer is laid out is with these wedges, these wedge-shaped structures, these so-called cassettes. And the idea is that we make these wedge-shaped structures quite large, and then we insert them in, and we make the full disc. And in the silicon-only part, this is what they look like. We have individual silicon modules that are hexagonal in shape. And then in the mixed layers, where you have silicon on the inside and then Scintillator tiles that are kind of trapezoidal in the outer regions. What I've spent a lot of my time working on are these silicon modules. And this is an example of one of them here, and I've kind of exploded the view so you can see internally. So there's this silver part, which is actually the silicon detector. Underneath that, there's a gold layer that is actually on a plastic thing called polyimide, which is an insulating layer. And then there's a base plate, which is actually copper tungsten. So it's incredibly dense, incredibly heavy. And sitting on top of that is this printed circuit board, or PCB. And then it's like a Swiss cheese. It has a lot of holes in it. And through each of the holes, there are these tiny wire bonds that connect the printed circuit board to the silicon. Now, printed circuit boards, to most people, including myself a long time ago, what's the difficult about those? You see them in every form of electronics these days. Why is it so difficult? Actually, making these ones with the holes is incredibly difficult. And we've been to various companies to try and make them, and many have failed. Now we've got a few that can actually make them, but they're still very, very difficult to make. In the end, we need 30,000 of those, so it's quite a big deal. We've made some progress. We've made systems based on these hexagonal modules. This shows you a little layout of what we call a daisy or a flower of 7, and then put them into beams in CERN and in Fermilab and in DAISY, and tested them to see if they actually work, and I'll come back to that later. So we've built quite large systems. In fact, the system we built in 2018 has more readout channels than the whole of the present Endcap calorimeter of CMS. So it's quite a big deal that we're already testing there. The way we're building these wedges is also rather complex. It's very tight, and this is where the mobile phone technology comes in, because we have to get the signals out, and we have to get control and power and so on in to these detectors. So these other objects that you see on top of the hexagons are power, readout, control, and so on. And then we have to have heavy materials to create showers, which I can talk about later if you wish, that go either side of these. So we make this double-sided object that when you look at that double-sided object from the side, so the green part here, the very bright green large part, is these modules that I mentioned, the silicon modules. And then there's all these other boards that sit on top of those. And then you have the heavy material, in this case lead, on top, and the space is really tiny. There's only just over 5 millimeters to get all of your connectors in, your services, your cables, your optical fibers, some pipes and so on. This is why I call it a giant mobile phone. It's not all tiny engineering. In fact, we took this photograph today to show the contrast in this single detector between some of the engineering. So you see on the right, some of the bolts that hold this 220-ton object together compared with some of the bolts that we use to hold these miniature parts together. So the contrast in scale is still mind-blowing to me. And indeed, with some of these big objects, they're really very difficult to make, and there's not many places around the world that can actually cope with it. So even just a steel plate, we're looking around the world, and at the moment this is a place in Pakistan that will probably machine these plates to the required thickness and diameter. You can see the scale of the machine compared to the size of the people. I mean, these are enormous things. Forget that. And this is one of the plates that we actually made, I think in the Netherlands, I can't remember now, I'm sorry, that were arrived at CERN recently. And you can see them being unloaded off the truck here under COVID conditions, of course. And then we were measuring them in a lab at CERN. And we have to get, over the course of this 5.3 meter diameter disc, a flatness of 0.5 millimeter. This is an incredible tight tolerance for some mechanical object of this size. Very difficult, very time consuming, and very expensive too. And then we have to put this all together. So then one of the most difficult challenges we have is just integration. It's fitting all the cables in. So we have this team of very young engineers where part of their work is developing mock-ups of the inside of the detector, but also the services on the outside to make sure everything fits together and can fit together. And just before I joined this meeting, I was in a meeting talking exactly about this, in particular this region down here that is notoriously difficult. It's very compressed, very difficult to deal with. So the big question, of course, after all of this is, will it work? And the quick answer is yes, it will. And that's not just a blasé statement and of hope. We've actually measured lots of things. As I mentioned, we put things in a beam in 2018. We start seeing images. We start seeing things that look like those simulations that I showed at the beginning, a bit like the bubble chamber pictures, where you can start to see what a muon looks like and compare it with a charged pion. And charged pions, some of them interact quickly, some of them take a little bit longer to interact, and then they do this thing called the showering, or electrons or positrons actually in this case, and we start to really see what's going on. We've also seen that if you sum up all the signals that we see in the various layers, do you measure the energy of the incoming particles? And we do. So it acts as a calorimeter. So we've made a functioning calorimeter. That's a good thing, of course. And we then start to see quantities like the energy resolution and position resolution and various other things, and match them to simulation. And the match with simulation, that's the difference between the red curve and the black curve on the right, for either the linearity on the top or the energy resolution on the bottom, is extremely good. So we can predict with some accuracy what our detector is going to do. So we've proven that it will do what we want it to do, which is fantastic. And now we can go ahead and do the detailed design. In addition to things like energy resolution, we start to do almost new physics with this. We start to see things that we've never seen before in a calorimeter. And that's down to being able to measure not only the energy, the signal size in the detector, but also when the particles arrive at the different layers of detector. And we measure this with a timing accuracy of tens of picoseconds. So this is limited at the moment by the electronics that we used in 2018, but it will get better. And on the right, there's the color code in there. It was an animation of a particle, how it develops, or a particle shower, how it develops in time. And this is the first time this has ever been done. This level of detail we've never done before. Finally, what's going on now? COVID, a big message that I think hasn't got out enough to the world at large is that COVID hasn't stopped CERN working. It's made it more difficult, of course, just like everybody else's life, but it hasn't stopped us working. So the example on the left is one of my engineering colleagues doing some work, posing for a picture as well, but he was doing some work on the structure that will support the high-granularity calorimeter, so doing some load tests to make sure it would actually do what it should do. The top middle picture is at my house, in fact, of me measuring some things at home, looking at some printed circuit boards to see if they conform to what we want. On the bottom is one of my colleagues, he was a technical student, measuring or characterizing 300 chips from his home and having the test set up in a drawer in his desk at home. And then there's me and a colleague, Andre, working in a lab, again with COVID precautions taken with one of our colleagues on Zoom, of course, telling us what to do or describing what to do. So it really doesn't stop. I couldn't give you, much more than that in the time allocated. I've already gone over my time. There's still a lot to do. In about 5 years from now, we have to install this thing during the long shutdown 3. But hopefully the times ahead will be really fruitful and we'll see some new physics with this detector. So just final word is to say thanks to the CMS collaboration for all that they've done in this, and in particular the HGCAL group. Thank you.
Thank you very much, Dave. I think we can all clap for you silently. So I have found this presentation really clear and very engaging. Thank you very much for it. I think we go now right up to the questions and comments. I suggest that people raise their hands, and then I just tell you to unmute and talk when you have a question. And oh wow, we already have a question. So then let's go ahead. So Michele, please, you can unmute yourself and ask your question.
Thank you, David. Congratulations for this nice presentation. I have a question concerning the production of the hexagonal PCBs. How are you organizing such production?
So, yeah, I know where you're coming from, obviously, Michele. So, in fact, until now, we've been just in the prototyping phase, and we've prototyped with a few different companies. A couple of them have failed in a couple of different countries. A few have just said no, they can't possibly do it. And a few have tried and have actually eventually succeeded. So at the moment we're prototyping still with 3 companies. And the aim in the next months is we'll produce a market survey and really go out there and look widely to see who can do this. It's not standard. It's very, very difficult to do. And then hopefully the aim is to get the invitation to tender around the end of this year or January next year. So it's an open tender. At least for part of it. It depends where part of the money comes from, of course.
Thank you, David. How many layers?
How many?
Layers.
This is only 8 layers, but the complexity is this stepped hole. This is really very challenging indeed.
Okay, thank you.
Thanks.
Thank you very much, Miguel. Now we have Alessandro.
Well, thank you. Thank you for your presentation, David. I would like to ask you a couple of questions. One is a bit theoretical. At the beginning, you mentioned a possible divergence from the standard model detected by LHCb with a value converging to 0.84, if I'm not wrong, instead of the predicted value of 1. Yes. I just wanted to ask you if, according to the standard model, the decay ratio of the B particles, the muons and electrons, should be exactly 1, or should it be lower than 1, taking into account the different mass of the muons and the electrons?
So I'm absolutely out of my depth to answer that with any certainty whatsoever. Being, you know, my expertise is really on detector design and construction and so on. My understanding, and Rebecca may be better placed actually to answer this than me, my understanding is it should be exactly 1.
Okay, thank you.
And the mass doesn't come into play in this.
If I may ask you a second question, you mentioned that in the coming years, the amount of data to be processed will be a huge amount of petabytes. I know that CERN is investing in quantum computing technology. I just would like to ask you, when do you think that this new technology will be available for analyzing data? And if you think that quantum computing will be used also to analyze backwards all the data already taken in the previous experiments in order to validate them and get the most of the data?
So let me answer it in a slightly different way. Let me go to the backup here. You're right to focus on the computing challenge. It's massive, and with the detector like the high-granularity calorimeter, the amount of information it produces is so large that present computers can't really cope with it, especially CPUs. So, and this sort of plot here on the left shows you the sort of computing challenge that we have, even just for producing Monte Carlo events, for producing simulated events, but also for the analysis and how it's going to grow in the future. It's just incredible. So CPUs can't deal with it. So we might get some factor with CPUs, but the chances are that we won't get enough. So we're already looking into things like GPUs and heterogeneous computing, you know, so very fast FPGAs and so on. And that shows a lot of promise. Already we're getting factors of 10 in various places. Now, that will hopefully see us through. But what that won't be able to do is the last part of what you said of going back and reanalyzing things. The power just isn't there. Now, there is indeed an initiative, not just from CERN, but from many, to invest in quantum computing to you know, improve the processing time by more orders of magnitude, so that we can then go and process things again. One of the big difficulties, though, isn't just the processing time. It's the sheer amount of data that needs to be shifted from one place to another. And that input-output is one of the other challenges. So even if quantum computing comes through with, you know, orders of magnitude on the processing time, it's the getting the data in and out that becomes another bottleneck. So if you compare it with things like the search for extraterrestrials, you know, that took off with this SETI at home thing, because the input output was very small, but the processing time was very large. In high energy physics, we have that additional complication of the input output. So who knows? I hope that, you know, there has to be something. We have to go further, because what we have at the moment isn't going to work.
Thank you.
All right, so thank you, Alessandro, for your question. So now we have Carmen.
Hello.
Hello.
Thanks for for your very good presentation. I'm also curious about the production of the Scintillator part. Do you have any news about that?
Oh, so I didn't include any slides in here actually about the production of the scintillator part. In fact, we've explored two different methods. One is cast scintillator and the other is molded. And for different parts of the calorimeter, we're choosing the different method. So we are looking at both of these, depending on the needs exactly. And I don't think we've chosen where the scintillator will be produced, but it might be an in-kind contribution from one of our collaborators or one of the countries, or a few of the countries. The scintillator itself is not too difficult. In fact, the number of tiles we need is enormous. So I think I had the numbers back here somewhere. Let me just, there we go. So there's about 240, 250,000 of these scintillating tiles. So that's quite difficult to deal with. Another one is we need to wrap each one of them a bit like wrapping a sweet to make them light tight. So there's a lot of emphasis on wrapping machines. And then each tile is read out individually using a silicon photomultiplier. So we have to connect the scintillator tiles on a board with the SIPM, with the silicon photomultiplier as well. So the integration aspect of this, putting it all together, of the scintillator part, whilst not quite as complex as these silicon modules, is still a massive challenge. So I think the scintillators themselves, not so bad. Everything else, pretty challenging indeed. I don't know whether that answers your question, to be honest.
Well, no, yeah, I have more or less an idea how this is going. You said, can I ask another question, or are we running out of time? I don't know.
Ask as much as you want.
You said that there are two types of tiles: the cast tiles and the molded tiles.
Yes.
What is the physics argument to use one or another type? What is the condition that should be met?
So I confess I do not remember.
Oh, okay.
Yeah, I don't remember. It might not be the physics argument as such. In fact, I don't think it is. I think it's more the shapes.
Okay.
And one lends itself better to like this this high density region than the other. Okay. But honestly, don't take my word for that.
Okay. Many thanks again.
$140 events pileup. So how are you going to deal with it? Is it time resolution sufficient to distinguish different events in this pileup?
Yeah. So so this simulation here is of 140 pileup events, and we deal with that pileup in two ways. One is spatial. So having this so-called high-granularity calorimeter, which gives us an X, Y, Z and energy view that's completely unprecedented in particle physics, will help us disentangle lots of this pileup. But the other thing is indeed the timing, and that's why I emphasize this timing at the end, because yeah, in this picture here, what this picture here shows on the right is one bunch crossing of protons and various collisions of protons within that bunch crossing. So each color is showing you a different bunch crossing. What you can see is that they're spread out in the horizontal dimension. And what that means is that particles coming from those different horizontal positions arrive at the detector at slightly different times, but really of the order of tens of picoseconds different. So our detector is designed to be able to measure things at that precision, so that we can tell whether an electron, for example, came from the purple collision point here, or came from the green one over here on the left. So this we know our detector can do, but it's a challenge, and in fact is why it's a challenge to the whole of CMS and the whole of Atlas, in fact, and is why, again, we're installing new detectors, those so-called MIP timing detectors, to see the time of arrival of single particles in the end caps and in the barrel of CMS, to be able to, again, track down which production vertex the particles came from. And both Atlas and CMS are doing that. It's a big challenge to sort of search for the needle in the haystack again.
I see. Good luck. Thanks a lot.
Thank you.
Thank you, Adam. So next is Donovan.
So thanks, David, for the presentation. I'm sorry, I don't have any camera on my computer.
That's okay.
So I have a question regarding the electronics. You mentioned at the beginning that radiation will be very important when the system will run. So how can you know in advance the impact of this radiation, and how to tell if the electronics will fail or not?
Right. So in fact, we have various facilities to test for the radiation hardness or not hardness of the electronics components. That's the first thing to say. So we can effectively put our electronics in either a neutron environment in something like a reactor. We can put them in X-ray sources, which gives you an ionizing dose. We can put them in spallation sources of neutrons at various places, like in Belgium or in Strasbourg. We can also put them into CMS in various locations. So we can actually put things, I don't know if you, hopefully you see my mouse, in a region around where my mouse is, and we can put them inside CMS and leave them for a year and then look at them afterwards and see how they are. So that we have these facilities that we can use to measure things, but we also know how to design electronics to withstand enormous fluxes of radiation of different types. So we can design transistors in such a way that they're quite robust against ionizing damage. And it turns out that the modern technologies used in normal CMOS technology for the chips that you have in your phone are actually very robust against ionizing radiation. We add to that by doing something called triplication. So for the logic inside some of the electronics chips, we don't just store a number in there in one location, we'll store it in 3 locations. And then we'll compare those 3 numbers. And if one of them changes, it means that potentially a particle has gone through and flipped a bit in one of the transistors and has modified something. But because the other 2 say, actually, no, it should be this number, we can flip it back. So we can do an auto correction function as well. So we have design techniques, and then we have the testing facilities to verify that the designs work. An example is a power chip called a linear regulator that we're developing actually for the high-granularity calorimeter. We've sent chips to Ljubljana to be irradiated in a nuclear reactor there. And at the same time, right now at CERN, in a facility, in an X-ray source, we're doing ionizing damage to those as well and seeing how they perform. And so far, everything matches expectation. And by the way, the simulation tools for the modern electronics, they allow you to study the effects of radiation as well. The biggest difficulty, to be honest, is that virtually no one else in the world, apart from the military, needs radiation hard electronics. So we're kind of on our own, and designing these chips is very tough these days.
Okay, thank you for the answer. It's clearer now.
Okay.
Thank you, Donovan, for your question. We still have 5 minutes before the end of this. I don't see any hands raised, so I can maybe ask a couple of questions if that's okay.
Really difficult.
No, it's gonna be fine. So I have first one question in a very practical sense. You had in one of your last slides the effects of COVID-19, right? So how has the pandemic affected actually things like deadlines and deliveries from people? Is something that you have managed to absorb well, or it has caused any kind of problems?
It's caused a lot of problems, that I'm sure you know. Right. It's caused problems in different ways. Firstly, it was for quite a long time difficult to get regular access to the lab, except for the lab being not only CERN, or let's say the labs around the world, not just CERN, but DAISY, Fermilab, all the institutes as well. Difficult to just go in and do some work in one of the laboratories, like this one on the right-hand side here. It was difficult to do that, and all we could do was just keep things running. So there, what we did was, we were imaginative. We moved things to our houses within reason. We didn't want high voltage supplies in our houses or big electronics crates and things like that, but within reason we could do some things. So we could still carry on doing some work, but it slowed down without a doubt. The other, so schedules are slipping, and there's not really a lot we can do about that. We keep up as much as possible, but we can't do everything. The other thing that's really hit is that, and I think it's hit CERN especially, is that CERN isn't just CERN people, right? It's not CERN employees. I'm one of them, but I'm one of the few. Most of the, at least for the EP department, they're people who come from institutes outside, and they're simply not able to travel. So they're stuck in whatever institute. I know, for example, Catherine, who's connected today, she's based at Brunel University in the UK and can't travel here. It's impossible to travel. So we miss the people that will do a lot of the work. So then a lot of the work comes down to people who are based at CERN, who aren't just the CERN employees, but a few people who remain based in the area. So there's a lot of stress on those few people that are still around. So it's hitting it, I think, in the long term in hidden ways, in increasing the stress load of the people who are here. And I'm sure, everyone's going through a similar situation. When you're working at home, it's not easier. It's harder. You feel a bigger pressure, a different pressure to just keep working all the time. And it's hard. So yeah, it's hitting us. It's hitting us all. Things will slip, but there's not much we can do about it. We have to stay mentally healthy and just still try and do what we can within reason.
I understand, and being involved in upgrade projects myself, I know exactly what you mean.
Well, I think even sorry to say, I mean, even with analysis, a big part of what CERN is that everybody here knows is it's like this picture on the right. It's not that me and Andre are working separately. It's we're discussing together, we're brainstorming together, we're figuring out things together. We're working with engineers and with technicians and sometimes with theorists to figure it all out together. And when you're doing an analysis, you want to work closely with other people. And that's just much, much harder to do now. And doing it via Zoom it's okay. It's better than nothing, but it's not quite the same.
Well, I mean, hopefully things will eventually get better. Let's not put any dates on anything. But
Yeah,
if we move on to the extreme future, since you're presenting a piece of technology that is really something very advanced and extremely cutting edge, now my question, to put your mind a little bit away of the current situation, is, are there any plans of using this kind of technology in future collider experiments or in ongoing experiments that are not high energy physics? Do you know about this? Can you tell us a little bit about it?
So in fact, the part of the concept of the HGCAL came from a collaboration called CALIS, which is the calorimetry for linear colliders. So there's been a few studies of linear colliders for the future to come after LHC, things like CLIC or ILC, the International Linear Collider, and so on, where they were looking at high granularity silicon-based devices. So a lot of our collaborators actually came from CALIS. Mm-hmm. And in fact, this beam test that I showed here on the right, the part that's under the black cloth is a CALIS Scintillator plus SIPM calorimeter that we borrowed and we used in our system. So a lot of people are coming from that community with a view to using this sort of technology in linear colliders in the future. But also, most of you have heard of the FCC, the Future Circular Collider, and that comes in two variants. One is an electron collider and the other is a hadron collider. Mm-hmm. In the hadron collider, the survival of silicon is tough. It's not obvious that it will work. And certainly for Scintillator, it's really not obvious how it will work. But for the electron variant of FCC, this is definitely on the cards and to use this sort of technology. So it's definitely there. So in fact, in where are we now? Beginning of April, in a month from now, there's a symposium that's organized by ECFA, the European Community for Future Accelerators, all about future calorimetry, so in the long term. And we're discussing different types of calorimeter that could come in the future. And I'm making a presentation on the lessons that we've learned from not only this detector that we're building now, but also other calorimeters that we're building to see what we can learn and see how we can go forward into the future. So yes, we hope that this is just the starting point.
It looks really cool. And I think it's really nice. And okay, I think it's probably a moment to wrap it up a little bit. Let's call for the very last question. If somebody wants to say the last thing, I'm gonna give you some time to raise your hand.
I just like showing that photograph, by the way.
Yeah,
because
can you tell us
one
about
of the people that's connected now.
Okay. I suspected it.
Yeah.
Okay, I see no more questions. Let me ask you the very last one, because I am actually curious about it. So when you were presenting the very tight space that you have to work with, I was always thinking about how you will deal with the cables and how will you deal with the cooling of that. And with the cables, you more or less already addressed it. But can you tell us how this is going to be cooled down? Because if it's 30, 35 minus,
so in fact, what I didn't draw on here is this, the orange part in the center there is a copper plate, and that's actually the cooling plate. So embedded in that are pipes, again, copper pipes that carry biphase carbon dioxide. So we're using this dual phase system for cooling the detector, just like is used in the pixel detector of CMS now, and I think in the inner detector of Atlas as well now. So this is definitely the future, or at least a temporary future, because we cool down to about minus 30, 35. But in the future, we'll need to go colder, and CO2 isn't the solution for that. It's incredibly inefficient at anything below minus 40. And then you start looking at things like ethylene, and ethylene has a big drawback in it's explosive. So you don't really want to use that in a detector. So we have to find new solutions for going colder than minus 30 before you get to things like liquid krypton, which is about minus 170. But there's this position in the middle between CO2 and krypton that's difficult. We don't know how to do that yet.
Thank you very much, Dave. So actually, I think that Simon may have the last question. Okay, so we take Simon and it's the very last. Rachel, are we okay with this? Yes.
Just quickly, just why does it have to be so cold?
So, a good question. So the silicon, the reason, or what happens to it in radiation, is that you damage the crystal lattice, and it's a semiconductor that's essentially a reverse bias diode. So you reverse bias it, and the diode doesn't conduct unless a particle travels through it, and then you get a signal. The trouble with radiation damage is you damage the lattice and it starts to conduct. So you get this, what we call a leakage current, and that current can then dominate the real signal. The way you can mitigate that is by cooling the silicon, and you drop down this leakage current by orders of magnitude. So every, I think it's 7 degrees that you go colder, you get a factor of 2 in the leakage current decrease. So by going from room temperature to minus 35, you go down by a couple of orders of magnitude. So you have, that's the only way. It's like a Lazarus thing. You bring it back to life by going cold.
Thanks very much. That's great.
Welcome.
Thank you, Simon, and thank you.
By the way, no one noticed, and I'm sure no one would notice, there was something in common between every slide. So I think this.
Dave.
Oh.
Well, announce there was something, because this is the competition I'm going to announce.
Oh, I'm sorry.
So it's all right, but no, it's okay. So because I'm just, no, go ahead, finish what you wanted to say.
No, I won't say anything then. I'll let Rachel comment.
All right. So I think we've overrun a little bit. I'm terribly sorry, but it was because it was just so interesting. Thanks ever so much to both Dave and Rebecca for taking part in our News from the Lab. And we can see that there's many, many exciting years ahead, I think. And I'd like to invite you back when you start the installation, if that's okay, and you can let us know how that's going.
Yeah, I mean, I might be underground then, but yeah.
Underground in CMS?
Yeah, absolutely.
Filming it, maybe we can have a video of it. So perhaps, you know, I think this sparks a great deal of curiosity. So I'm going to be publishing the video. So if anybody has any objections, please send me an email if they don't want to appear in the video that I'm going to put online. And then I'll also be sharing Dave's slides online. So there's a competition. Not only did Dave put a huge amount of effort into making the slides and making it really engaging for us, but he's also put something in the title of most of the slides, I think it is, Dave, isn't it?
Yeah, all but one.
Yeah.
Apart from the ones that don't really have a title.
Okay, so what the challenge is over this Easter weekend, because we can't really do much, is to have a look at the slides and then see if you can find out what it is that links, or what the slides have in common, what it is that does that. And then you can win a special CERN alumni gift.
Oh,
Yeah.
I didn't get a gift.
But you haven't, or you've done it now, Dave. So I was going to say afterwards you will do. So anyway, I'm sure that if you have any questions, I'm sure you can contact both Dave and Rebecca on the alumni.cern platform. And if you've got any suggestions for any other topics or any other talks that you'd like us to focus on around CERN, perhaps in different experiments, different areas, then please let us know. And then also just please let us know what you thought of this talk, how we can improve it, and any other suggestions that you might have, or questions, etc. Just please do get in touch. And now all that remains to be said is for me to say, I hope you have a very nice Easter break, and you eat lots of chocolate, and you stay safe.
I think I've eaten enough over the lockdown, to be honest.
Say again?
I think I've eaten enough chocolate over the lockdown and over the past 30 years, so I'm not sure I need any more.
Substitute chocolate with whatever you like. So thank you, a really, really big thank you again. I think we can do the same thing, applauding everybody virtually, and also thank you so much to both Rebecca and Dave for taking part. And we really look forward to seeing you. We're trying to organize these with a frequency of about once per month. So keep your eyes on alumni.cern. Thank you very much to everybody. Take care.
Thanks a lot. Thanks for the questions. It was great.